If 10 to the minus 3 molarity of a strong acid is added to water, what is the equilibrium pH at T equals 25 degrees Celsius? Okay, it might not seem like we're given a ton of information, but I promise we can solve this problem. Since we're not told what type or what exactly the strong acid is, we'll just use the generic form of the equation. HA, that's our strong acid, is going to go to hydrogen ions plus the conjugate base. Okay, now we don't actually really need to know what this conjugate base is since we're solving for pH, and pH is just dependent on the amount of hydrogen ions present. Since we're told it's a strong acid, we know that this completely disassociates, which some of you might be relating to right now. But basically what that means is that in terms of unknowns at equilibrium, we're going to have just H plus and A minus from this equation. But remember that water is itself a really, really weak acid. And that's going to form hydrogen ions, and also its conjugate base is OH minus. Okay, so technically we have another unknown at equilibrium, which is OH minus. All right. Now we're going to solve this problem two ways. The first is what I call the scientist way, which is fully true and correct. And then we'll solve it with the engineer's method, which is maybe like 95% true, but also like 5 steps quicker. So let's get to it with the scientist way. Nothing against scientists, of course. Okay, so we've got 3 equations, got 3 equations, we have 3 unknowns. We need 3 equations. Okay, so let's get started. We know that we're at 25 degrees Celsius, so that means our kW for this problem is equal to 10 to the minus 14 molarity squared. And then that's going to be equal to H plus times OH minus. Okay, this is always true for water at 25 degrees Celsius. Okay, so our second equation, let's go back to our chemical equation. Okay, so we've got, let's say I have 1 molecule of HA, it's going to form 1 molecule of H plus and 1 molecule of A minus. So from stoichiometry, we know that the amount of HA added equals the amount of conjugate base at equilibrium. And we're actually told how much HA is added, right? Our strong acid. We're told 10 to the minus 3 moles is added. So that means this is equal to 10 to the minus 3. Okay, and for equation number 3, also from stoichiometry, if you remember, we need to conserve charge as well, right? So initially we're starting out with neutral charge, and then we have a bunch of charged ions. So what that tells us is that these charges, the charges at equilibrium, have to balance each other out. So that means the amount of positive ions has to equal the amount of negative ions. Okay, so we've got 3 equations with 3 unknowns. Remember, our goal is to solve for H plus here. So what we can do is rearrange equation 1 to say OH minus equals something related to H plus. So from equation 1, we have OH minus equals KW, which we know, over H plus. Okay, and then if we plug that into 3, we're going to have H plus equals KW over H plus. And then we know our conjugate base is 10 to the minus 3. So this is from 3 and 2, technically. All right, and this is just a quadratic equation for H plus, and so we can solve this, and we'll get H plus is equal to 10 to the minus 3 moles, which tells us that pH is equal to 3, okay, because of the relationship between pH and H plus. pH is negative log base 10 of H plus. Okay, so that's where I got that. All right, nothing wrong with this at all, but let's think about this from an engineer's perspective. We've got a strong acid. Water is a weak acid. So if you think about it, this water is going to form a really teeny tiny amount of H plus, whereas the acid is going to form a much larger portion of H plus. So really, if we get rid of all of this, I think I can do it in just this little space. Really what this means is that the amount of H plus and A minus at equilibrium from HA is going to be so much larger than the amount of H plus and OH minus added from water. So really, the only significant part in terms of finding the pH is just how much of a strong acid we've added. All right, we got a strong acid, it's always going to beat out a weak acid. Okay, so if we do that, then really all we need to know is stoichiometry, right? HA forms H plus plus A minus. If I have one molecule of HA, it's going to form one molecule of H plus and one molecule of A minus. So this tells us, our stoichiometry tells us, that HA added equals H plus formed at equilibrium. And remember, we couldn't do that at this step, right? So here we had to relate HA to A minus because, remember, this is all about changes, right? So the only place I'm adding in A minus is in the strong base, the strong acid. So I can make this relationship. I couldn't say that HA added equals H plus here because I also was counting H plus from the water, right? Okay, so here we can do that though because we no longer care about what the water is doing. So HA added equals H plus formed, which means that at equilibrium, the concentration of H plus is just equal to how much we added, which is 10 to the minus 3 moles. And then take the negative log of that and we get pH equals 3. Okay, so technically not as truthful because we're making an assumption that the weak acid water has a negligible impact on the final pH, but we get the exact same value.